Welcome back to our exploration of recursion in SQL. Let's reap the fruit of our labor now. We have introduced the semantics of the recursive CTE in the set-based union and in the back-based union all case. Let's put that to use now and explore a number of use cases of recursion in SQL practice. So this will be a series of videos now in which we explore different scenarios in which recursion can help or can even be the only way to express a particular problem in SQL. Okay, so let's consider our first use case of recursion in SQL. We will tackle something that we have described before and a problem that we tried to solve before but couldn't. Now with the presence of recursion, this will be perfectly possible. Let's take a trip back in time and recall our array-based encoding of trees, actually of forests. As you can see, this is a forest of two trees, the forest T3. This is something that we would like to represent. And back then we used arrays to represent this. So if you flip back through the course slides, flip back to the part where we introduced arrays and you will find our discussion of this array-based tree encoding. Okay, so that was actually very simple. We would like to represent the structural information in these trees. All right, so 2 is a child of 1, 3 is a child of node 2. All right, and we would like to represent the labels of these nodes. So as you can see here in these tree diagrams, I have separated the label information in an isomorphic little tree on the right hand side here. So the node with number 6 has label F, and the node with number 2 has label B. So I hope you can recall the semantics of these tree diagrams. Okay, we represent the structural and also the label information in terms of arrays. So all the information about this tree here, the tree T1 here, is found in this single row in our table trees. Okay. So what we find there is, of course, is the tree identifier, but also a parents array. So if you look up the parents array at index I, you will find the parent, the node of the parent of node I. So let's look at index 3 here. The parent array indicates that the parent of node 3 in table T1 is 2. So let's check. The parent of 3 in tree T1 is 2. Okay, that's perfect. The parent of 1 in tree T1 is, well, there is none. 1 is the root node. And we can see that here there's indeed a null value recorded as the parent of node 1. Okay, so I hope you can recall how that worked. So this is the labels array, which is synchronized. So if you find the parent's information at, say, offset 3 inside this array, you will find the label information at offset 3 as well. So let's look again. The node number 3 in table T1 with parent 2 has label D. Okay, so the node with number 3 has label D. Yeah, that looks good to me. Okay, so this is the array-based encoding of trees in our table trees. Okay. So now we wanted to compute the nodes on the path from one particular node in the tree, any node in the tree, up to the root. Okay, so if we are looking at this node number 6 here, it's the node labeled F. Then the nodes on the path to the root would be 5 and 1. So 6, 5, 1, that would be the path to the root from node F. If we look at node F over here, then this is the label F. It's associated with node 2. So the nodes on the path to the root from this node are 1, 4, 6. So this is a 4 element or 4-node path. It has been a 3-node path here, and in general, well, the length of this path is only determined by the structural information of this tree. So we have to explore the child to parent relationship step by step until we reach the root. How far we have to explore, well, I don't know. It's really a property of the structure of the tree, all right? And we can only explore the child parent relationship one by one, and we would have to iterate this child parent relationship one step by step until we reach the root. This is a perfect opportunity to flex our with recursive skills in SQL. In fact, back then we had the conclusion that our current SQL construct, the construct that were current at that time when we were talking about arrays, were not sufficient to express this node to root path traversal. It's a different thing now. We can do it now, and how we can do it is actually explained here on this slide. Let me take a sip of coffee. So indeed, we will use the with recursive CTEs to compute this path information. All right, so what we will compute here is this path table, okay, with 2 columns. In the first column, we will just see the tree identifier, T1, T2, or T3, right? In the second column, we would find a node number, so these integer node numbers that we have used in the trees. And if you look at all the rows inside the path table, then you will find all the nodes. You find all the nodes that are on the path from the node labeled F upwards to the root. Okay, so this is in fact a sort of invariant that we would try to establish in this path table. If there is a T, N pair or tuple inside the path table, then we know that node N lies on the path from node F to T's root. Okay, so this is an invariant, and I can only encourage you to think in such invariants when you try to explore such recursive queries. We will come across such invariants again and again, and I think you will find it useful to think in terms of these invariants to assess the correctness and the meaning of these recursive queries. Let's try that on this particular query. So we would start off this recursive computation, of course, with the base case. Okay, and since our traversal of the path starts in the F node or in the F nodes of the respective trees, well, that is exactly what we would do. We would look at all the trees. We would record their identifier in the tree column. And then we would look for the node number, for the index of the node with label F among the labels array here. Array position, I hope you can recall this built-in function. It would just return the element index of this element here, of the F element among the elements in this array. This is just the labels array. So this will be the node number of the node labeled F. All right. So for each tree, we will just emit one row, the tree number and the node number of the F node. Okay. And this fits with this invariant. We would find a pair inside the path table that records the tree ID T1, T2, or T3. That's okay. And it would record the node number of the F node, which is indeed on the path from the node F to T's root. It's just the beginning of that path. F is on the path from F to its tree root. So that would be the start of the whole recursion. And then this would be the iterated recursive part. Okay, as you can see, it's indeed self-referential because we are looking at the paths that we have explored so far. Okay, So these are the paths that we have explored so far. Let's marry that with the tree information, with the structural tree information in our trees table. And of course, only consider path information with the respective correct trees that we've stored. This is this particular predicate here. All right, so we have explored in a particular tree, we have explored a bit of path already. We will now get the overall trees encoding, of course the correct row in the trees encoding. That's why we use this particular predicate. And now in the select clause, we've got all we need. We will create a new entry in our path table for this one particular tree that we're currently looking at. We know that we have explored the path up to this node already. This is the last node that has been added to the path. So recall that in the path table here, you will find the information that has been added during the last iteration of our recursive query, or you will find the information that has been added by the space case. All right, so this is the node that we have reached last on our path. We will just look up in the parents array where our path will lead us. So this is just the parent of our node. This is the next node in our path, and we will record it as such. So this is the next node, the parent node that we have now reached in our path traversal. And that's all there is to it. This is the next entry in our path inside our tree t.tree. Okay, of course, this will be added to the overall path table. And this newly found information is being passed into the next iteration of our recursive query down here. Okay, you see that we are using the set-based or union-based semantics. So all knowledge that we have explored so far, that we have found so far, is not recorded twice. Well, these traversals will lead us from some node F step by step towards the root. Actually, there shouldn't be any situation where we find the same parent or path information twice here. Okay, so there should be no issue with duplicates here. Still, we will see that using the set-based variant of the semantics is quite crucial here, and we will see why on the next slide, where we will trace the whole computation and then also see why it comes to an end and how it comes to an end. Okay, so here we go. Let's focus on a single tree. Let's focus on the T1 tree only, right? Things don't get significantly different if you add more rows here with path information in different trees. Just try it out. So for exposition purposes, just let's look at one single tree here. That's the tree T1. So if we evaluate query Q0, then that query would go on a search for the node labeled F in this particular tree T1. And if you recall, it's exactly this particular node. It's the node with number 6. And indeed, this is what you find after Q0 has done its job. The base case has done its job in tree T1. The node 6 is on the path from the node labeled F up to the root. It's the node F itself. Okay, right. So this arrow actually indicates the position of our traversal from the node up to the root. Currently, we are at node F itself. This information is fed into the recursive query for the first time in this particular case. Well, this query will use the parents array to look up the parent of this particular node inside the parents array, and it will find node 5. Indeed, if we look for the parent of node number 6, it's node number 5. So this would be the next node that we add to our resulting table. And it's the last node that we have explored. It will be the next node fed into the next iteration, where of course we will find 1 as the next parent that we will add to our exploration. So this is the next entry in our path table that we will add. Okay, so our traversal has already led us to the root. So, okay, so this is being fed into the third iteration of our recursive query part. This time, a lookup in the parents array will lead, for node number 1, will lead us to a null value. That's what I try to indicate here. So there is no real parent node for the root node. What we will get in the parents array lookup is a null value. And indeed, this is the value that we are recording here. So there's already 4 entries in our path table now. Okay, this is the entry. This single row is the entry that is being passed into the 4th iteration here. Okay, right. So this is our current position in the tree. We were at the virtual null node, or above the root node in a sense. We would use this particular value, the null value, this null value, to make a lookup in the parents array. And that lookup will yield null again. If you recall our discussion of arrays and array lookups, then an array index of null, looking up an array index of null, will just yield null again. Okay, so looking up the parent of the null node will yield null again. So what we will find in this particular iteration will be our path has led us in tree T1 to the null node, this null actually. So, but this is information that we had before. T1 is associated with null here. T1 will be associated with null in this 4th iteration. This is not new knowledge. It will be removed. And after removal, this is all we are left with. An empty table has been computed in this 4th iteration. Okay, so this is the indication that the iteration has to stop. We have computed the empty table in an iteration. Looking at the semantics of the CTE with union semantics, set-based semantics, this is the end of the entire computation process. So it has been crucial. It has been crucial that we were removing information that we have found already, namely this information, that we were removing that from the result of the 4th iteration. This led to the empty result and thus to a termination of the entire recursion. If you add up all these intermediate results, then this is the final table that we are left with. So in tree T1, indeed the nodes 6, 5, 1, they lie on the path to the root. All right, there's also this spurious entry with the null here. Maybe in post-processing it would be appropriate to just remove this particular entry from the final result. That's what post-processing is for exactly. Okay, so let's switch over here to the terminal, where we find exactly this setup. This is our trees table. Let's create it. It's just the trees table that we have seen in our discussion of array-based tree encodings. These are the tree sample trees. We have seen this before in the lecture and also on the previous slide. This is the array-based encoding. There you go. Okay. Now let's see. This is just the recursive exploration tree query that we have just discussed on the slide. No changes there. This is the exact copy. And you see that we start our traversal in the node with label F. Okay. Yeah. No further post-processing here. I'm just ordering the entries by tree because, as you see, we are actually performing this traversal for all trees at once. So in all trees, we are starting at the node labeled F, if there's any. And well, in all of these trees, we would then perform the traversal separately. Okay, right. Okay, so this is what we get. So in tree T1, we indeed find nodes 6, 5, 1, which are on the path to the root. Of course, we also find the spurious null entry. In tree T2, we find 1642. 1642, this is exactly the nodes that are on this 4-element path from the node labeled F up to the root. Okay, and the spurious entry. And well, the forest 3, T3, can only contribute this spurious entry because there is no node labeled F inside the forest T3. Okay, so well, these spurious entries, of course, they are somewhat nagging me. So maybe it would be time for some post-processing here. I would maybe disable this post-processor and then instead use this here, which almost does the same. But well, I'm just disregarding any entry that led us to this virtual or spurious null node. And if we evaluate this, then well, yeah. So these are the path from the F node up to the root, and this is the same in tree 2, and tree 3 does not, or forest 3 does not contribute at all, just as expected. Now, if you look at these entries here, 6, 1, 2, 4, of course, they are not ordered in any useful way. Let's switch back to the slides once again and look at the sample trees, tree T2, for example, where the path actually should read 2, then 1, 4, 6. That would be the proper path from the node labeled F up to the root. So 2, 1, 4, 6. What we found here is something, well, it's 2, 1, 4, 6, of course, but in some random permutation. Well, that's all well and good, but I would rather prefer an ordered path that starts with 2 and ends with in this case, the node 6, which would be the root node. And of course, we can modify our query to do just that. We would just have to record the position of this particular node in the path that we are constructing. So let's augment our SQL query to do just that. I have sketched this on this slide. So now this is the computation that we would like to perform, right? In the query Q0, in the base case query, we would like to not only record that there is the node numbered 6 in tree T1 that would be part of the path, but because it's just the beginning of the path, it would be at position 0, okay? So this is something I would like to record here. The next node would be found at position 1, and the next node would be found at position 2, okay, 0, 1, 2, right? So that would be useful in reconstructing the order of nodes on the path. Our traversal has already reached the root node, as you can see. Now, if we follow the computation scheme that we have developed, then of course our next traversal will lead us to this virtual null node above the root. So that would be the entry that we record, right? Well, in the third step on the path, we would reach the null value, okay? So now we would expect the whole thing to come to an end by now. But well, in the next iteration, well, what we would do is, of course, explore the parent of the null node, which will give us the null node again. But our counting of path steps will probably just continue, and you see that we've added 1 in each iteration to the position, 2, 3. We would probably do the same in this iteration, right? And we would end up with an entry T1 for null. This is an entry that we have never seen before. We have seen T13 null before. T14 null is new knowledge that we have never seen before. We would add it to the final result, and this row would make up the result of the 4th iteration, which would then be passed on to the 5th iteration, which would find the row T15 null, which would then be passed to the 6th iteration, and so on. The whole thing just wouldn't terminate. Okay, so the generation of new rows is something that will spoil the termination, the nice termination logic that we had in our original query. And let me remind you that this is a common source of bugs with recursive queries. So this is one case where it's rather easy to step into the trap and produce queries with unlimited recursion. Okay, so of course, now that we know that we are prone to step into this trap, we can avoid to step into it once we implement this over on the PostgreSQL side of things. So let's do that. Right. Okay, so this is the version of the ordered path construction where we maintain this explicit POS information. Okay, so that will be a 3-column table will be constructed. Okay, let's see how the base case query Q0 looks like. Well, we will of course record the tree identifier. We will start with a position of 0. Okay, this is the beginning of the path, right? And of course we will again start at the path, at the node label F. Nothing has changed so far apart from this starting position information. Okay, so in the recursive part, this is the recursive part. Well, the overall structure of the computation has not changed. We will look at the path and see how far we could explore it. I have explored it already. We will join this with the trees information to get hold of the information of the parent information that we need to continue the path. Of course, we will make sure that the correct trees is associated with the correct path that we have explored so far. That tree identifier is recorded here. We will increment our path position information because we have found the next node in the path. We have found the next node in the path, and we will of course explore the parent child information just by a lookup inside the parent array. Nothing has changed so far. But as you can see, we have added this conjunct here, this conjunct. All right, so we will make sure once we have encountered the virtual null node above the root, once we have encountered this particular node, we will end the entire recursion. You see that this predicate forbids or disregards these null entries once they are found in the path. Okay, so a null entry here will not qualify against this particular predicate. This predicate in its entirety will be false for these null values, and we will not yield any further step on such path anyway. All right, so any path that has reached the virtual root node or the node above the root that is encoded by p node equal to null will be terminated by this particular carefully added condition in this where clause here. Right, so this is all we need to ensure proper termination. Right, and well, yeah, so let's just try this out. It should work. Without this, we will have endless recursion. So be careful. So let's do this. Okay, so no endless recursion. That looks good to me. Now we have some proper ordering criteria in our path. That looks better to me. Okay, so indeed we have found path in tree T1 and we have found path in tree T2. We have proper position information. All of this is ordered now 0, 1, 2, 0, 1, 2, 3. This is a 4-step path. Indeed, we start at node 2 and we end at the root node 6. All of this looks good to me. Okay, so yeah, this is ordered path traversals. Nice. One final tweak that we could envision is that, well, we could have collected the path information differently, right? This is one path in the tree T1, but it occupies 3 rows. We could just have a single row entry here and collect all the participating nodes, all the nodes that have been found on the path 651 in an array of node identifiers. That array would be able to represent the entire path in a single array value. So we would need only a single row for the T1 tree here and a single row for the T2 tree. That would be nice. And of course, the positioning information would be implicit in the array. Well, we would just look for the node numbered 6 at the first array position. This would be the second, this would be the third array position. No need for a particular explicit POS encoding here in this third column. This looks like a good plan, I would say. Let's look at this modification of the query first on the slides here, just to make ourselves aware what we are trying to compute here. All right, so well, this would be the setup now, right? Yeah, so we would start in tree T1. We are only looking at tree T1 here again. We would start our path at the node number 6, right? So the path that we have explored so far, would be empty, all right? Okay, in the next recursion step, we would add the node that we have reached so far. We would add it to our path, okay? And then use the parents information, the parents array, to move up in our tree traversal, to move up from node 6 to node 5. This is indeed node 5 that we have found here. Okay, so this is the plan now. So this is the information that we have found in this particular iteration. That's new information that we've never seen before. Okay. In the next iteration, we would just add the node that we have reached so far. We would add it to our path and, of course, explore the tree further, right? In the next iteration, add that particular node that we have reached so far, add it to the end of our path. So a nicely ordered path is being constructed, 6, 5, 1, okay. Because we have been at the root already, the next step would lead us to this virtual node above the root, which is the null value here. Okay, we would now use a predicate like the one we've seen just in the terminal and have a predicate that ensures that we stop exploration of the path once we see this null value as the last node that we have reached. This is the indicator that the computation has to end at this particular point. So we won't generate this particular entry anymore. The predicate will keep us from entering the next iteration of our recursive query and then producing this result. This will not be generated. Okay, this is the first point here. Ensure termination with the predicate, just like the seen in the version of the query that had the explicit POS column. Okay, right. And now for some post-processing. So as you can see, this and this and this and this, all of these, they have been added to our overall result table, right? Well, we have accumulated the path information inside this array here. Actually, this entry, this has all the path information that we need. These partial paths that have been explored, well, that's nice, but they are actually not needed. They're actually not needed to represent the entire path. Post-processing should actually remove these entries from our accumulated result. And we can easily spot and easily identify the path, the complete path information that we want to keep. It's exactly that entry added to the accumulated result table that has this null entry here, this null indicator in the node column. Okay, so that would be the indicator, that would be the criterion that we look for if we would like to identify the complete path information among the partial path that have been accumulated in the overall result. This is the second item here in our discussion. All right, so let's switch over to the terminal one more time and see how this is being implemented. Right, so this is the implementation. It's again this 3-column table that we are constructing, tree identifier, the last node that we have reached so far in our exploration, and the path that we have accumulated so far. Okay, in the beginning that would be the empty path. Okay, and when we enter the recursive part of the query, everything has stayed the same, including this particular predicate that keeps us from iterating forever. Okay, because we would just accumulate longer and longer path arrays, arrays that we have not seen before, and the termination would never be reached. But okay, this ensures termination. All right. And we would just explore the parents array to find the parents of the current node, and that current node would be added to the end of the path that we have found so far. This is the path we have found so far. We will just elongate it and add the node that we have reached at the end to the end of this particular path that we are constructing. And that would be all about it. Post-processing would look among all the paths that we have been accumulated. It would identify those entries that have reached the null, the virtual root above the root, the virtual node above the root node. Okay, and this is exactly the indicator that this row in the path table will contain the complete path. So let's do that. Oh yeah, that looks nice. So these are the paths. These are the paths that we have explored in the 3 trees. You see that even the tree 3 is represented with its empty path, which I would argue is the proper representation of a path that just cannot be explored or traveled. All right. So if I now remove this where clause here, you will see without proper pre-processing, we will see more entries in the resulting table than we probably need. But what we do see is how the paths are being incrementally built up. So maybe that's nice for exploration or explanation purposes. See, we start at the empty path and build and concatenate to its end until we find the entry that completes the traversal. All right, so let's activate this again. And I think this concludes our discussion. If there weren't this particular quiz question, oh, it's another quiz question, please post to the forum. Please post to the forum and try to provide an answer to this question. Can you adapt the last query? Of course, I'm talking about this query in which we accumulate the path inside an array. Can you edit or alter this query that we can form, well, multiple paths during traversal? So we would like to explore the path from, say, node labeled F and labeled E inside our trees. That would lead to 2 paths in the T1 tree, and it would lead to 2 paths in the T2 tree, and so forth. It would be the path originating in the nodes F and E. Well, of course, generally, can we modify this query so that we could traverse the root path from arbitrary nodes in these trees? And if you think about this and find a proper solution, please post to the forum. I would love to read. Probably everyone would love to read about your comments and thoughts there. You will find, if you explore this, that the modifications to this particular query are indeed minimal. Okay, so which is a nice indication that this is indeed a set-oriented way of thinking about recursion. It's not just about, well, we follow this particular path through the data. No, these queries can explore all paths from an arbitrary number of starting points through such tree or graph structures. We will explore graphs in further examples later in this chapter. I hope you stay with us, and I will see you soon. Bye.